Hey everyone, it is my first time at PyData, so I'm excited to be here. Yeah. All right, I'll go ahead and get started. Just like to give you an idea of who I am so you believe me as I'm talking to you. So I am leading the curriculum development at Metis. I'm also an instructor there. I primarily focus both in deep learning in general, as well as ethics and data science. My sort of focus in GANs is maybe about a year or two old. In addition to that, I work with a local nonprofit, Tiva Tech, leading free workshops around here. I also wanted to say, so Justin Blender is a student of mine. He graduated, I believe, 4 months ago. And so this is, what you'll see today is actually a continuation of a student, his final project. And so what happened is, as students tend to do, he had an extremely ambitious idea for his final project. And just because of time and because of he had literally just started working in data science 3 months before, he wasn't able to fully see it to its end. And so what I've done is added, I'll show you, you'll see the whole thing, but I added one relatively new normalization technique, and then sort of what the title of the talk is about, a process that allows us to condition GANs based on multi-label data. And so those are the things that were missing from the project as he sort of finished it up a few months ago. And yeah, I'll show you sort of the final product. Unfortunately, Justin can't be here. I wish he could. So I wanted to signpost a little bit. Like I said, this is my first time at PyData. I don't really know, I don't have a great feel for where everybody's at. I don't know if we're all TensorFlow experts, writing code that gets accepted at NIPS, or if we're sort of new to all of this. And so this is where I've been aiming, and if it's a little bit off, let's just adjust it. So I want feedback. I want to make this as interactive as possible. It's a tutorial. Teaching is what I do, so hopefully we can figure that out. So I'm aiming for people who basically understand the fundamentals of deep learning. So you could probably explain, maybe with some effort, these ideas: backpropagation, stochastic gradient descent. Maybe are familiar with common loss functions and different tools that we actually use to build deep learning models. If not, there's going to be a fairly quick review, which of course we can slow down. There's a whole room of whiteboard if we want to talk about this stuff. I'm also sort of aiming for people who have used recent deep learning packages. So we'll be doing all of this in keras, which I think is the most accessible one. I might have been that. I'm a little bit frustrated. PyTorch is also quite accessible. But yeah, we'll be using one of the really modern packages. So if you're unfamiliar with that, there might be a little bit of a learning curve there. And again, just stop me if you get to a line of code or something that seems unfamiliar or difficult to explain. Can I get a show of hands? How many people have built a generative adversarial network in anything here? And it's okay, yeah, so just a handful, I guess. So I'll try to make sure I'm providing something for everybody, folks who are new to this idea of what a GAN is. I mean, folks who are interested in some new techniques. So by the end of the talk, if we all accomplish our goals, I want everybody to be able to do these things. So the basics are understand and explain what's important about generative adversarial networks. So what makes them different from other networks? What makes them go? What are the parts that if they were missing, it would break? I'm also going to be giving you boilerplate code that hopefully you'll understand well enough to at least adapt it for new purposes. So maybe you have a data set of your own that you want to use on this, and it's not the data set that I'm teaching. Hopefully you'll have enough understanding to actually be able to do that. So we'll be talking a little bit about state-of-the-art techniques in GANs. I don't necessarily expect everyone to understand or be able to derive spectral normalization by the end, but I will expose you to a few things. And the big thing I want on that end is when you leave here that you're at least better enabled to do your own independent exploration. So if you see a new concept, there's 3 months left in the year, who knows what's going to come out. And so if one of those new developments happens, hopefully you'll be better enabled to do your own exploration of like what that is. Maybe building it out in your own code, maybe looking at other people's implementations of something new and making sense out of it. So does that sound good? Does that sound off, like significantly off from you guys? Cool. All right, so what we're going to do now is a deep learning review, and this is something that, I mean, you could have a semester-long course over this. We're going to try to do it in, I don't know, 10, 15 minutes, and so maybe less than that even. So this is going to be fairly quick. If anybody is like completely lost, please let me know, because I can like absolutely take my time. This is absolutely one of my favorite topics to teach. I don't have that many slides on it, but we can always add material. So the sort of common structure of all deep learning models is a chain of differentiable functions. And so it might not be obvious, but here you can see I'm starting with, this is sort of the common nomenclature for deep learning models. And so X is going to be our input data. We've got just a variable here, but we typically batch it together. So like a series of images, series of rows, whatever your data looks like. And so that there with the Wx plus b, that's just what we call an affine transformation, like a linear transformation. So this is, if you've ever had a linear algebra class, this is the sort of basic building block of that class. And so, if you can see here, we're just using these building blocks. F is our just like general function to build our hidden layers. And those are the H's, H0, H1. And we'll build n of them. N could be anywhere. I think there's no like dividing line for a deep model, but typically n is a few to hundreds. Many of the modern models have hundreds, dozens and dozens of layers. And so the important thing to understand about deep learning and the way it works, and an especially important thing for the tutorial coming up, is that all this is a chain of differentiable functions. So we don't really care what f is, like eventually the details matter, but just in general when we're starting out, f can be anything as long as it's generally differentiable. And so what that means, we can actually look at this from the traditional application perspective, sort of like where deep learning started, where we have tabular data. You might have seen presentations on that traditional application here, where you have like rows, maybe a pandas data frame with rows of data. You have your features, that's your input, that would be x, and then you're predicting a y. And y can be a number if you're doing regression, it can be a classification. But the really cool thing about deep learning is because that first definition, that it's just a chain of differentiable functions, is so loose, we can actually set it up to do some really impressive, quite different things from that tabular data to prediction. So one thing that we can do is image to text. You might have seen those automated captioning systems. They're really, really cool. That's completely different from that traditional application if you think about it. Image to image, there's a few of these. Super resolution is one of them that's really cool, where you take an image, essentially like add pixels, guess what those pixels would be if the image had been downsized. What we're going to be doing with GANs is sort of even a step below this, which is going from nothing or a random data distribution to images. We're just going to be generating images randomly. And this flexible structure of deep learning is really what allows us to do that. So that's like a general, it's a really high level abstract point, but it is like quite important for understanding how this works. So what are the important ingredients? So we're sort of building this extremely like tall or deep network here. And then we're going to use these two tools to actually make that useful. So stochastic gradient descent is not limited to deep learning. Actually, essentially, many, if not nearly all of the data science models that you use can be adapted to use gradient descent. And so yeah, it's a general principle that actually just allows you define a loss function that measures performance. And stochastic gradient descent just finds the adjustment to the parameters of your model that minimizes that loss function. So if loss function is, if the higher it goes, it's bad. If we use stochastic gradient descent to minimize that loss function, we're going to be improving things. And so once we do that, then the whole ball game is no longer, it's no longer the details of like setting up your model or pre-processing by hand. It's really setting up this chain of functions and your loss function so that as stochastic gradient descent minimizes that loss function, you get something useful. So it's a very different sort of approach to traditional data science approaches, where if you've ever done, if you did computer vision before maybe like 2010, it was a lot of pre-processing by hand, a lot of these like setting things up very, very carefully. And it might seem like a totally different world now, where really we just set up a deep learning model that could theoretically do all of those transformations that we used to do by hand. It could learn them, and then we just let it learn whatever transformations are the best. So yeah, that's stochastic gradient descent. Backpropagation is just the piece of the puzzle that allows us to do gradient descent at each layer. It is literally the chain rule of calculus. It's just an algorithm for that. Yeah, and it applies it to many layers. Yes?
How's gradient descent different from like a standard convex optimizer?
It's not necessarily. It is. It's not convex is the only difference. Is stochastic gradient descent can apply to extremely non-convex functions. And for one, there's a lot of papers. I don't have the citations off the top of my head, but you can show fairly straightforwardly that deep learning models are necessarily highly non-convex. So they have tons of local minima, and it's like a huge problem. And yeah, so part of like getting these things to work is setting it up so that A, your local minimas are pretty good, and B, you don't have to get stuck in the bad ones. But yeah, you can actually, so an example of a convex optimization problem is support vector machines. Many implementations use SGD as part of that.
Is there like a separate SGD library if I just want to do the optimization?
That's a good question. I don't know. I know I have code somewhere in my computer actually implementing support vector machines in TensorFlow, using TensorFlow's stochastic gradient descent. It's not an efficient implementation, but it's just demonstrating that you can use that. And I know that there are people online that have that as well. Cool. Any other questions? It's sort of like a very high level look at deep learning, but I sort of like want us to have these concepts, sort of be comfortable with them before we get into the nitty gritty of what GANs are. Cool. Cool, yeah, so that's all of deep learning really quick. Yeah, so we'll get into the code a little bit more too. I think I set this up to be like a little bit of a loose set of slides so that I can get a feel for where everybody's at. And then we can dig into the code. We can add things if anybody has questions. Okay, we're going to talk about GANs in general, but before I really dig deep into what GANs are specifically, I want to talk about convolutional classifiers. So I mentioned earlier that computer vision has changed drastically in the last couple decades. This right here, convolutional classifiers, is exactly why. This is the tool that sort of like revolutionized that, that field. And so what we're doing with convolutional classifiers is we're setting up that chain of differentiable functions. And a convolution is just a differentiable function that learns a feature mapping. And so that's what this image, if you've like looked at any like image recognition in deep learning papers or blog posts, you've seen something like this. And so what's happening is we sort of, at the very left, we have our input, which is the robot image. And this, I don't know if I'm off camera or whatever, but this right here is just the feature map. And so what convolutions do, I wasn't planning to go into the math, but we can talk about it a little bit if somebody wants to. We're essentially passing that feature over the entire image. And so whenever that feature is present in the image, it activates. Whenever it's not present, it isn't active. Often it's somewhere in between. And so the important thing is that you see those layers. They're like several sheets of paper or something. That's just to signify that we're learning several feature maps. So we might have one for vertically oriented edges, one for horizontally oriented edges. And so what we're doing is we're sort of setting this up so that the network, the deep learning network, can learn these features. That's the first step. And then we're actually using either sampling or pooling. We'll talk more a little bit. We'll talk a little bit more later about what those mean. But once we learn those features, we're actually summarizing the image in terms of the height and width. We're shrinking it using sampling and pooling so that it actually is forced to combine those features into bigger parts, essentially, until it gets down to that whole that it's able to make that prediction on. Yeah, and so convolutional classifiers typically, or always, I guess necessarily, because they're a classifier, end in some classification vector. So if this is your typical classification problem where you have, if you've ever seen like the digits classification, you have 10 possible numbers. It's a vector of 10 probabilities. That's the output of this model. If you've looked at ImageNet, what all the fancy hotshot models are trained on, you got a vector of 1,000 classes and 1,000 probabilities. So let's look at a little bit closer actually what's happening here. So this is a different way of looking at that same setup. So this, I actually didn't mention it earlier. A lot of my images, I have the citations in the slides, but typically they're either from Chalet or Ian Goodfellow's books. So this one's from Chalet's book. I really, really like this way of thinking about convolutional filters. So that's our image there on the bottom. And so like what's happening is the network is passing these filters over it and saying like, that first one is just like this weird like curved edge. And so that filter will become active every time it sees a curved edge. And then we have that like downward sloping edge. And then we have maybe this like black triangle in the middle. And so all of those filters are essentially telling the network, all right, this is where this feature is in the image. And the utility of sampling or pooling to shrink your height or your pixel height and pixel width as you go through the network, the utility of that is it forces it to summarize those subparts into parts, and those parts into even bigger constituent parts. And eventually, you get that process down to a whole that you can make a prediction on. And you can sort of see what this looks like whenever we look at feature visualization, which is, ooh, I don't know what happened there. All right. So yeah, I've been talking about these convolutional filters. One way to think about actually what's happening here is to take a filter and ask, all right, what input image would make that filter the most active? And so this is sort of like a cartoon representation of like a sort of rightward curving line. But you can imagine what it would look like if we said, what is the image that maximizes that filter? And it might be one of these that has a bunch of rightward curving lines in it. And so that gives us an idea of what that filter's looking for. That one's just looking for that texture. We can actually put those edges together to get a series of edges, and that's what this illustration is calling a texture. You can put textures together for patterns. And so this is from left to right is where we go from input image down through that deep network. And as we go to the right, I don't know what's happening. All right. As we go to the right, we're getting closer to that prediction. So it's pulling more and more whole data out of that image in preparation for that prediction. And if I can I zoom in on this? Yeah, this comes from a really cool, I've sort of hinted at it, but a really cool demonstration of how this works. But in the bottom right, you can actually see, this is from a real network. It's actually like learning dogs eventually. And so those are like cute little puppy faces. And that's like the image that's the input image that most activates those filters that are closely related to predicting dog. And so you can sort of see like what it's looking for when you think in terms of that. And that gives us a better idea of how it works. All right, so that is a very, quick overview of how convolutional classifiers work. Does anybody have questions about that or anything that feels like uncertain or uncomfy? Maybe if you've never heard of a convolutional classifier, this feels like a whole lot. I'll tell you, like, I was building successful image recognition models in deep learning before I actually understood any of this. So it's not an essential part to understand it, but I think it helps a lot. So you've got the code, you can actually just put the code together that does this, whether you sort of understand or appreciate that process, and it still works. So yeah, I guess what I'm saying is fear not if it feels uncomfortable, but if it does and you want to talk about it, I wanted to open it up. All right, so we're ultimately working towards generating images. I've gotten as far as talking about how to classify images. That's kind of the opposite. So now let's think about how generating images would work with these same puzzle pieces. So we've talked about using convolutions plus what I called pooling or subsampling to shrink an image. This is sort of a visual representation of what it looks like to actually use convolutions plus the opposite of that, either upsampling or what is technically not correctly called deconvolution. In keras, we call it convolution transpose. But we actually use those to progressively grow an image. So essentially what we're doing is we're taking this process of image classification and running it in reverse. So we're starting, this is still our input, but rather than shrinking the image as it goes down towards that hole, we're actually going to be increasing it. We're actually going to be blowing it up. So here, we'll talk a little bit more about what that input is or what that means, but we're just going to give it a random noise vector of, it could be zeros and ones, it could just be values drawn from a bell curve. So here we've got 100 length vector, and we're going to reshape that and then run a convolution on it over and over again. And if we upsample between convolution runs, we actually get a progressively larger image that we're forcing to learn how to generate a plausible replica of the training data. So again, we'll see in code. I feel like some people it helps to have these visuals, so I wanted to make sure I have them in there. Sometimes it's a little bit easier to see in the code what's happening. So yeah, just to recap, so we've talked about convolutional classifiers, we've talked about convolutional generators, really briefly, we talked about convolutional generators. So GANs, what GANs do, sort of their value, is putting those together in a very useful way. One way historically to do that is actually to skip the GAN process and just have what's called an autoencoder, something that takes in an image, summarizes it down to a vector, and then blows it up. And so you can think about that as our zero starting point. And that has some drawbacks that we can go into if people want to, but I didn't include here. So GANs work this way. We sort of set up these two teams. This D here, this D function is called, is for the discriminator. And then G is for the generator. So if you want to sort of attach these to images, this will be G here, the thing that's blowing up a vector into an image. And then this will be D, the thing that's taking an image and shrinking it down to a useful vector. So the way we set these up, we set them up in sort of a game that they play against each other. Where the first task for the discriminator is to take that X sampled from the training data and just learn to classify every training data image as one. And it's a really easy task. You know, alone it could do that perfectly. As you might guess, it could just guess one for everything. So that it becomes challenging when we build the generator, the other half of this, which is we're asking it to generate plausible images from the training data set. And then you can sort of think about the discriminator's task as getting both this original image, which is on the right, and then this generated image on the left. And then we're asking the discriminator to say, like, all right, which of these is real and which of these is fake? So now the generators, or the discriminator's job gets a lot harder. It has to tell the difference between these two images. These are selected to be, it's a little bit easy to tell which one. The right one is a little bit more pixelated, I think. But you can see how it's not a trivial task now. It's no longer, there's a challenge there. And so we have this input noise vector z, which G actually uses to generate that image. And then we have an X sampled from the training data. And then D tries to make that the images from the generator, that's G of Z near 0, and then the images from the training data near 1. All right, so that's like, yeah, this is sort of boxology here. Maybe that's not the most helpful. So I just want to like take a pause from talking about networks a little bit and just like talk about like what this task is. So I mentioned that autoencoders just try to recreate images. They try to summarize it and then recreate it. If you've ever done principal component analysis, it's basically the same thing as what an autoencoder is doing. A generator is doing something fundamentally different from what an autoencoder does. A generator isn't taking an image and then like summarizing it so that it can recreate it. A generator is trying to reproduce that training data set in a meaningful way. So let's think about the CIFAR data set. Has anybody used this CIFAR data set before? It's a very cute data set. It's 32 pixels by 32 pixels. We'll use it in the Jupyter Notebook section of this a little bit later. But the nice thing about it is it's small enough so that you can run things like in the amount of time that it takes to like, I don't know, go get a coffee or finish a sentence sometimes. So this is a frog from that data set. And so you might think about what if your task was the generator's task of fooling somebody and making them think that the thing that you draw, the 32 by 32 pixels that you draw, is from the same set of data that that image is from. How would you do it? Like what color would you make the frog if you had to do that? Does anybody know? Excuse me? Yeah, like what color would you make your frogs if you had to generate frogs from the training data?
Green.
Green would be a good guess. Yeah, I think green is a great guess. This one's a little bit brown, I think. So maybe greenish brown. I think most frogs are probably going to be on the ground, so we might do like a greenish, mostly brown though background with like some green specks in it. That might be our frog drawing process. But if you think about what the generator's task is though, the generator is going to get hundreds of these. And so looking at that same data set, you can see our friend here in the top left. So this is the exact same data set. These are the first 100 frogs in CIFAR. Let's think about like what that discriminator's task is going to be. So if you perfectly replicate this image, if you get really, really good at drawing these like 32 by 32 pixels, and then the generator sees your image and a bunch of them, and then it sees this set of images, do you think it'll be easy for the discriminator to tell what's real versus what's fake? Could you? Like what if you put yourself on the other side? If you were the discriminator and I drew 100 of these, and then you were comparing it to 100 of these, and you had to guess, all right, which of these are the real images and which of them are the fake? What do you think your accuracy would be?
Depends on how good the generator is.
I don't think so. If we can perfectly replicate it though, if we could just like copy this, like download it onto a thumb drive and then upload it every time the discriminator asks for an image. Excuse me? I could get it right every time except for once. And here's how. Is I would say every image that looks exactly like this was generated by the generator that memorized that image. And then every image that isn't like that is from the training data. And the only one I would miss is that one in the top left-hand corner, because it looks exactly like the memorized image. So do you see, like it's that sort of like simplest understanding of the task, actually like the generator would lose every time. So what the generator actually needs to do is it needs to be able to generate hundreds of these that look like they're from the same set of data as this. So the generator is not memorizing images and just reproducing them. It's actually learning the entire distribution of that training data. And it's trying to reproduce that distribution. And that's a hard task. Like, I'm saying distribution, it's sort of like a mathematical term here. But what we mean by that is the world. Like, we actually, like, these are just taken by real people of real frogs in the real world. And so the generator is trying to understand how that world works and generate images like that, which is quite the task. So yeah, it's learning that distribution of the training data. So what that means, what we get from that, is that's like, it's an abstract point at first, but what we get from that is something super duper cool. So we get this like truly meaningful understanding of the training data. An autoencoder, like the JPEG compression algorithm is an autoencoder. It just shrinks an image and then it blows it back up. It doesn't understand how the world works. But if we do it right, a generator really does. And so what this is from one of the early deep convolutional GAN papers. What this is they took, so in that first column, they took all of the men with glasses in the data set that were, sorry, I'll back up. This is all from the celeb data set, the celeb A data set. And that's what we're going to be using here in a little bit. And so in this paper, in this deep convolutional GAN paper, what they did is they took all of the men with glasses and they just like averaged up the vector that was used for those. And they did all of the men without glasses for that. And what you can do for that generator is that you can actually use this vector math and you can say like take the starting vector, the man with glasses, subtract the man without glasses, and then add woman with glasses. And what it actually learns is that, okay, there's this direction that's gender, and if I go in that direction, I'm going along this like male-female spectrum, whatever that means. And then there's this glasses spectrum. There's this with and without glasses spectrum. And if I travel along that spectrum, then I get people with and without glasses. And so if I take man with glasses, subtract man, and then add woman with glasses, then I get woman with glasses. Yes?
Am I correct in assuming this only works because they're cropping the image for headshot, right? There's a background.
Ooh, it makes it easier. That's a great question. So if anybody didn't hear, we were asked like if this only works because it's cropped. Maybe this paper only would have worked if it was cropped. In general, like one really, really recent paper and one that actually inspired the second step that we're about to get into, I think the sort of hashtag or whatever is BigGAN, BIGGAN. They use the original ImageNet data set, which is just like things out in the wild. So nothing is like very tightly cropped like this. It's like real live images, and it does really well, like shockingly well. So yeah, it doesn't have to be cropped, but I cropped the images that we're going to use. It makes it a heck of a lot easier. But yeah, so this vector math seems a little bit hokey, maybe, if you've never seen it before. Anybody who's done word embeddings, though, has anybody seen word embedding math? Yeah, this is the exact same idea as word embedding math. So it can be pretty cool. So yeah, all right, so we've got GANs, hopefully under our belt. At least we feel a little bit more comfortable with them. The really important thing that I want us to understand is like what it means to actually learn this distribution. We're like learning meaningful qualities about like how these images are generated rather than just how to stupidly reproduce them. So I've got two more topics I wanted to cover in the slides. We won't go into detail on these, but rather than switching from slides to notebook to slides to notebook, I wanted to just like at least point these out before we dive into the notebooks, and then we can be in the notebooks for the rest of the session. Okay, so the first one is this wacky idea called Lipschitz continuity. Did anybody like watch the Rugrats as a kid? Like Lipschitz always makes me think of that. So it's an annoyingly complex idea, but like we can sort of simplify it as understanding. So the Lipschitz constant is like if you have a function, it's the maximum rate of change of the function. So I'm going to use the board. So does anybody, who knows the definition of ReLU, the rectified linear unit?
Yeah.
Yeah. You can shout it out. Yeah, so I'm getting some hand motions. The hand motion is basically this, right? So it's roughly f of x, roughly, it's exactly, is equal to x, comma, x greater than 0, and it's equal to 0 else. Right? And so this is like, we would draw our origin right there. I'll make it a little bit neater.
I can use sigma.
Excuse me?
It doesn't really usually have sigma for instead of f.
Oh, maybe. Actually, you're probably right. Yeah, I was just using the general function term. But yeah, I don't know that for sure, but I'm sure you're right. So the reason I drew this up here is that we can just like think really quickly about, for some simple functions, what the Lipschitz constant is. So what's the maximum rate of change of this function? 1. Yeah. So so the rate of change here is just 1. And so that's the maximum. That's the maximum it ever gets. So for functions like that, for this one, it's like quite easy. Try to do that with like tan h, and it gets a little bit trickier. And so all the Lipschitz constant and talking about this concept does is it gives us a vocabulary to talk about like how quickly derivatives change. And if we can define a sort of limit on the derivative of a function or the gradient of a function as long as we're using it. So this relates to a problem that's encountered in a lot of GAN cases where it often is, like the discriminator's job is sort of objectively a little bit easier than the generator's job. The discriminator is just comparing these images. Often, like anecdotally, like you can make a really simple small discriminator that beats these like huge generators that have tons of parameters that it can sort of tweak to get slightly better. And so often there was a suspicion by the authors of this paper that I think, yeah, I linked to it in the notebooks. I meant to link to it here, but I forgot. But the problem that they were suspecting is that in many cases the discriminator essentially becomes perfect. That it just figures out the generator's game, and there's no way the generator can win. And in that extreme case, if you think about it, like what's the gradient for the generator? If it's never going to win and there's nothing it can do to change that, its gradient is flat. So there's no way for it to improve. There's no way to climb up the mountain to improve. It's just like a straight wall. And so what spectral normalization does is it actually is a normalization method that constrains that Lipschitz constant. And so it says like, all right, we're going to normalize the weights so that there's no way that they could ever be greater than 1, or the Lipschitz constant of that function could be greater than 1. So yeah, it's actually like a fairly, when you look at it at that like high level, it's a fairly straightforward idea. I implemented that code in keras. There's a couple others that have it implemented. I wrote my own that's like fairly simple. It's like one of the more simple ways to do it. So we can actually look at that code here in a minute. But this was the big new development that I added in. And this is actually what I was talking about to whomever asked if you had to crop images. So this is one of the big additions of that big GAN paper that allowed them to really successfully generate ImageNet images. So the last sort of like advanced GAN topic that we'll talk about really quickly is conditional GANs. So there's this general observation that goes back like years from like Ian Goodfellow that you can use classes whenever you're generating these images. You can use classes to add signal to that to the process of learning what the distribution of the data is. And so you can think about it as maybe in our, let me back up to the frog one. I don't have an image up here with all of the different classes, but in sci-fi there's 10 classes. There's frogs, airplanes, trucks, cars, cats, dogs, deer, and there's a couple, I'm probably missing a couple. But the generator, before it starts, doesn't know that there's 10 groups of things. For all it knows, there could be 1,000 groups of things. The there's actually a companion data set called CIFAR 100 that actually has 100 groups of things. The generator doesn't know that distribution ahead of time of the classes. And so at minimum, you can sort of imagine that giving the generator that really useful information, saying that like, all right, here are 10 classes, and this one belongs to that class, as it's trying to generate images, that could actually like help it quite a bit. And so, so both the generator and the discriminator benefit from that extra data. You get quicker in terms of the wall clock time learning. You actually have to do a couple more steps in training, so the training process takes a little bit longer. But if you like measure it on your watch, learning happens quite a bit quicker. And the cool thing is we don't have to do that complicated like vector math that we were doing with like man with glasses, woman with glasses anymore. We can just say like flip this bit upwards, and then now we have a person with like dark hair or light hair. And so I wanted to just like really briefly go over the way I implemented this in the model, and then you'll see the code in a little bit. So here are two auxiliary classifying GAN schemes. The first one was originally limited to single class classification. So that's the AC GAN architecture. There's a really good paper on it. It's really common in the field. And fairly recently it hasn't been that popular, but there's been an addition to this called the VAC for Versatile Auxiliary Classifier GAN. And so what they did is they actually built like a third network. So we're talking about GANs with two networks. They just like added this classifier network over there and just trained that totally separately. And so what that does is it allows you to, it frees you up from single class classification to allow you to do anything that you can run classification on. It can be multi-class, it can be multi-class binary, it can be multi-class binary plus regression if you wanted to. And so that's been really handy in my work, just because like the single class classification is great for a lot of the standard data sets, but it's a little bit frustrating when you want to classify things like with these like interesting like non-traditional labels. And so like the CELEB data set, for instance, has binary labels, many binary labels. And so what I've ended up doing is almost exactly the versatile AC GAN, but I've actually combined the classifier and the discriminator. And so all I've done is just separated them at the very last layer. So in essence, it sort of has that same contour of the three separate models here, but in truth, it's one model for the discriminator and classifier, except for the very final layer. All right, and before we get into code, I wanted to show everybody some results. So this is the input training data of CELEB. You'll notice like I cropped them, but you'll also notice that with this crop, you still get quite a bit of like interesting variation. You get some people whose faces are totally to the side. They're all pretty lined up. And so here's some of the results that are generated, and maybe you're far enough away that they look really good. These are trained on just like the cheapest GPU that you can buy on AWS. So they haven't been trained on like the big Google TPUs yet. But you can see we actually get like quite good results, and they're fairly significantly better than the way reduced ones from just a couple years ago. They're more detailed than these. I haven't trained them as long, so we have a little bit more artifacting, but you can sort of see some of the benefits there. And the really nice benefit is without the matrix math, we can, at a really large scale, replicate the binary label manipulation. Yeah?
How long does it take to compute this relatively small data set?
To generate, this takes about 2 seconds to generate this set of 100 images. Probably less time. That's just like ballparking it. This trained for 10 hours, and it was about an hour an epoch. So yeah, this is just 10 epochs of training, which gives you an idea of how fresh this network is. It can train quite a bit further. But yeah, I wanted to show you manipulating these bits. So this one, you can actually see if I flip back and forth. This is just the random, the label vectors completely randomized. Some people are smiling, some people are not smiling. If we change it so the right side is all smiling and the left side is all frowning, you get a pretty significant, if a little bit difficult to notice change. So you can pick out some of the ones on the left that are smiling, and they're definitely not smiling in the second one. So here's the first. So maybe look at this person. This is a group of a bunch of smilers that are all going to get changed. And then we can just like really easily arbitrarily change them to not smiling. The second one is easier. This is eyeglasses. So almost nobody's wearing eyeglasses here. So we put glasses on everybody. What was the next one? Bangs. Bangs are another really easy one to tell. So now we're giving everybody bangs. And yeah, so there's 40 labels. So we can do this with a bunch of labels. So yeah, that's just demonstrating what putting all these pieces together can do. So thanks. And well, before we get to the notebook part of it, does anybody have questions though? Yes.
Why is it called adversarial?
Yes, that's a great question. So it's called adversarial because it's actually the reason it works is here we've got the discriminator and the generator working against each other. And yeah, it only works if they are like relatively evenly matched. They don't have to be like exactly, like the discriminator always wins basically. But yeah, yes.
The last set of photos, those photos were generated.
Yes,
faces.
exactly.
I'm confused how you got the same face then with glasses or without.
Great question. You'll see it in the code because this is actually how I set up the code. But we have two parts to generate every face here. We have a noise vector that's just sort of like random noise. And then we have the feature vector, which is all of the binary features. And if we fix that noise vector for every single image, then we can essentially regenerate that same image. And if we only change the feature vector, then we can say, like, what would this person look like with bangs or with a bald head or something? Yeah, great question. Yes?
Just following up on that, so like feature vector, you already kind of talked about what's in that type of labels that you discussed, but what makes up the noise vector?
Yeah, for that one, it's kind of like wide open. So in that big GAN paper I mentioned, they actually go through using a bunch of distributions. Typically it's normal, maybe it's uniform sometimes, but they used a binomial to sort of like randomly flip bits. And actually found that one works better, and like almost nobody uses that as an input distribution. But yeah, it can be essentially anything. Yeah. All right, I think, yeah, you right there.
What's the difference between the spectral normalization you mentioned and like gradient clipping?
Yes, that's a really, really good question. So I don't know if we have time to get too deep into it. So there's a couple methods prior to spectral normalization that have been really helpful for GANs. And so one of them has been gradient penalties and then weight clipping. Are you talking about either of those, or are you talking about gradient clipping specifically? Yeah, so gradient clipping is a specific technique, honestly, to make deep learning work numerically. Because gradients can tend to sort of like vanish even in like well-designed networks. And so gradient clipping sort of makes sure that we never get like a huge spike in the gradient or something like that we can't take the derivative of. But yeah, gradient penalties and weight clipping essentially tried to accomplish this indirectly. And so if you've seen anything on like the Wasserstein GAN, the Wasserstein loss applied to GAN, all of those essentially had to use gradient penalties in order to work. And this is just a computationally efficient way to accomplish that directly, of making sure the gradient doesn't exceed a certain value. Yeah, I think you're next.
So is there any attempt to apply this architecture to domains other than images, such as, say, generating poetry or fake keras?
That's a really good question. So, not that I know of. Yeah, for like generative, like NLP works actually quite a bit differently. You're still estimating the training distribution, but you're estimating like word transitions typically, or like you're essentially in effect estimating like a really long Markov chain of like these 10 words preceded like what next one, and you're sort of estimating that distribution. And so yeah, NLP, like recurrent neural networks have been doing that for a while, like directly and really, really well. But yeah, I don't know of like any of these like GAN techniques specifically for NLP. Yeah, we'll take a couple more questions and then we can start on the notebooks. Yeah, I think you had your hand up. Yeah. Oh no, you right there in the striped shirt. No, you, Tony. I thought I saw your hand raised. Oh no, you like him. Okay, never mind. Yeah.
Wait, is this like the reason for like mode collapse and stuff, or is that totally separate?
Ooh, so do you want to tell everybody what mode collapse is?
So like mode collapse is like, because it's trying to predict a distribution, the generator can like find a mode and keep sort of generating around there and do well without having lots of variation. So if it's like generating celebrities, here we see lots of different skin color, but maybe it'll do a lot easier, like, oh, I'll just generate lots of like, maybe like white males, for example, because there's more images of that in my training set, and do good in there, but yeah.
Yeah, no, so that's a great question. So mode collapse is like the bane of generative adversarial networks. It's super challenging. And so yeah, that's roughly what it is so often you can think that like it's trying to generate a lot of different, mode is just sort of like, you can think of it as these like ideals, or these like, you might have like this kind of person and a lot of like people that are similar, maybe like old white guy is a really big mode here. But typically the modes are a little bit more specific than that. I mean, you can see it, you can imagine a generator that sort of has 2 or 3 of those models for images that it's trying to generate at the same time. And then stochastic gradient descent says like, okay, if you go closer to either of those, you're going to improve. And it essentially just picks one and it has to combine that gradient improvement for both of those modes. And so typically for mode collapse, you get like faces that really look like they're a mashup of 2 or 3 modes like on top of each other. And it looks really ugly. I know spectral normalization is supposed to help out with that significantly. In my experience, it does. I don't have a great explanation as to why. I don't see how that would be related directly to the slope of the gradient. But also, yeah, in general, those beyond just like constraining the gradient, spectral normalization is a regularization technique. So it constrains like what the discriminator can do. It holds it back. So that independently of the gradient might be helpful. Okay, yeah, so let's get started on the notebooks really quickly. I wanted to at least show everybody. We've got about 35 more minutes, and I want to have time to open it up for questions again. So I put this URL up here, and that's where actually like everything is located for this class. So you can follow those lesson links for the notebooks. And before anybody like downloads it and runs it, I wanted to show everybody a couple caveats. So you'll notice that the link to the lesson goes straight to this collab.research.google. Who's used that before? A lot of people. Awesome. Well, if you've ever like been hard up for GPU cache, this is your friend. For now, at least, it's free GPU access. And so it's one reason I linked to this is because a lot of this is only interesting if you can do it at scale on a GPU. Doesn't really work that interestingly on a CPU. So after you load that first notebook, you can go to change runtime type. And you can say, all right, Google, let me use your free GPUs. And it's literally that easy. So yeah, now we're all going to be running on something that would take like a couple $1,000 to buy and install on our own computers. So that's cool. The other thing is that in some of the later notebooks, let me back up. We're here. Yeah, particularly this lesson 3. So if you wanted to skip ahead or look at these, this one is going to have you download a couple gigabytes of data. And even this one, if you like haven't used Keras's data set package, it'll have you download data as well. And the thing I want to sort of like red flag for everybody is that you absolutely under no circumstances should all do this at the same time on like the Wi-Fi that we're all using, because it just won't work. Like nobody's Wi-Fi will work. And so if you want to run this notebook, I've like put it on Collab to sort of like force you into using it on Google servers that they can sort of distribute the load intelligently. And so when you get to that second one, if we like end up running out of time or whatever, I put a note here, but in order to get this to run correctly, you'll just want to uncomment these and then run them. And that'll download the data, the cropped version of the Celeb data set that I put together just for you. It's a couple gigabytes. It takes like 2 minutes to run. Okay, so that's all the prep we need to sort of like get these notebooks up and running. Has anyone had trouble like finding the website? Does that work for everybody? Cool. And I think you might need a Google account or a Google Drive account to use this collab service. So I apologize if I'm forcing you to do that and you didn't want to. Oh yeah, also you will get, if you change it to GPU, so like I said, you'll typically get this. It's like a warning. We're going to run it anyway. So the very first thing is just installing a display package. We'll see the fruits of that labor in a second. But yeah, we're just like running apt and pip to install those two things. All right. Now that that's done, we're gonna pull in all of our PyLab stuff, and yeah. So now we're in just like standard Jupyter Notebook land, which at PyData I expect everybody to be relatively familiar. Let me know if you have any questions about the interface. Oh, also I'll turn on a keycaster in case like anybody wants to know like what is happening. So you can see like as I run through here, the shortcuts are a little bit different in Collab. So yeah, your escape A doesn't work anymore, but some of the other ones do. All right, so yeah, like I said, we're gonna be running this on Sci-Far. I've got a lot of the text that I went over in the, I've got a lot of text sort of covering what I went over in the slide portion. So I'm going to skip over most of that, but you've got actually the code to generate, for instance, that frog image of all the frogs, if you want it. So everybody, we can all download this simultaneously because we're on Google servers, not our own local ones. It'll take a couple seconds. All right. Yeah, so the first thing that we're going to do, there's minimal pre-processing required, which is one of the nice things about using a existing data set. The big thing that we're going to start out doing is scaling our images so that they vary from -1 to 1. So those are just the pixel values. And I'll show you why that's important later. It'll be a lot more clear. The other thing I'm going to do to set things up is typically in keras, I don't know if anybody has seen code that maybe you would be used to sort of seeing like a list of convolutional layers like this. And then like if you had like several of them, you might do that. I didn't do that because we're going to have like several similarly instantiated convolution layers. And so we're going to use Python's func tools to set that up. Has anybody used that before? Oh. Yeah, func tools are really, really cool. And so all it does, if you're not familiar, it's not a problem, is it takes these parameters and it just crams those into this function and then calls the function. So it's a great time saver. So all of these, we just have several lines of conv2d and then defining the same number of filters, same kernel size. And instead of writing that out every time or copy pasting, we can sort of write it out like this. And then now we have this handy function conv that calls keras layers conv2d and fills it with all of these parameters. And that, as you see just a couple cells below, makes our code very, very, very clean. So yeah, we're going to grab the number of classes from our Y. It's just going to be 10, but if we wanted to change this to CIFAR 100, it would automatically update. And then we're going to build this convolutional network. And so this is building out. If you haven't seen this before, this is this is Keras's layer representation, and it is literally equivalent, at least in general, to this representation of the slide that I showed. So you can see here, now you've got the numbers on it, that we're starting out with a 32 by 32 image, and we're shrinking it down to 16 by 16. The information that we're learning is actually, it's storing it in these channels. And so that's like, those are the filters that we were talking about, those, or the feature maps, sorry, the feature maps we were talking about. Yes?
So, and this is a colleague who used keras, he said, oh, it's so easy to design any network you want. And I look at this, all I see is com, right? Like, I can throw in 5 more convolutional layers if I want to. It might generate garbage. How do I know, like, or how do you work on that, I guess, the art of designing?
Ooh, general, I have a blog post on this somewhere. Yeah, that's a really, really good question, and I don't want to take too much time to talk about it, but the #1 rule for like deep learning tip that I can tell everybody is start with something that exists and works verbatim, and then change it from there. That's like, if anybody leaves the room with like any advice, like that's at the top of my list. And like you can like you can ask my girlfriend, like I spend so much time tweaking this shit because there's like so many parameters that it's like so easy to get lost, and like you mess up one parameter but you're changing 5, and then it's now the rest of the night that you're taking up to figure out like which of those parameters is the one, and like what do you change it to. So if you just start out, yeah, with something that exists and works, and then you can like change it piece by piece, scientifically a little bit. And I say that with a little bit of sarcasm because I personally fail to do that so many times. And yeah, this is just one that I know that works. It's not necessarily coming from anywhere. You can also notice general patterns. And so the one that I was talking about at the beginning of successively sort of shrinking the image is really important. And so that's all we're doing here. You also see another common attribute that you'll see in the last notebook is that the features typically increase as the size of that image representation decreases. And that's so that the image can store a similar amount of information as it processes through that network. And so here we're not doing that. We're just like setting the same number of filters for every layer. And so it's actually like losing information capacity with every layer, which is fine. This is a sort of a toy model just to demonstrate it. So we installed PyDot so that we could print these, and this is just like a different like visual way of looking at that, looking at what's happening. All right, I'm going to set it up, and I'm just going to use the defaults. So I'm going to use Atom as that stochastic gradient descent optimizer. Atom is just a like a couple wrappers around vanilla SGD. And then if anybody's ever used scikit-learn or anything like that, we're literally just going to fit this. Like we've built it, we've compiled it, and then in one line we're going to fit it. And so this is just like all I'm doing right now is reviewing like what it looks like to build a convolutional classifier. So this is using that CIFAR data set. Maybe like 20 years ago, this was an extremely challenging data set. Right now, with like a model that we could probably store like in a couple megabytes, we're going to eventually get up to like 80% classification. And again, like the images are just like a complete mess. So it's like really impressive to get at that level of classification. If we really wanted to tune it, we could get much, much higher. Yeah, I'll let this run a little bit. I've got it running for 10 epochs. But we don't need to take all of that time. Oh yeah, the other handy thing, if anybody has not used keras, I'll just point out a couple just extremely handy parts of it. We're passing it this validation data set, and it's going to automatically run, it keeps track of our accuracy on the training data as it's training, and then it's automatically running the validation at the end so that we can compare it. So we can see at the beginning it's underfit. It's going to stay underfit until sort of the very end. And we're going to end up doing pretty well. I'll pause that. I don't want it to run too long. I originally sort of made it as an exercise to add in layers to improve it. I don't want to take up too much time on that, but I'll leave that. You've got the notebooks. I'll leave that to you at home. You've also got like my website and therefore email. So if you want the solutions, you can email me. But I'm pretty sure you can figure it out. So here, yeah, this is, again, in text, a lot of what I said during the slide. And so you can see, like, this is the general contour of a deep convolutional classifier. It's starting out with this input image, in our case, 32 by 32. Oh, I didn't. I usually remember this. Does anybody know what the 3 means? Like, why we have 3 initial channels?
RGB colors.
Yes, it's the initial color channels. So that's why we start out. And so we're essentially like taking those 3 color channels and expanding them to 50 feature maps. And they don't necessarily have anything to do with color. So yeah, and this is that general contour. We can potentially add BN, stands for batch normalization, or pooling, or strides to eventually narrow that down to like 4 by 4. And then at the very end, we have a dense layer for that. Oh my gosh. Oh, this is I never edit in Collab. That's interesting. Yeah, this is that dense classification vector that I talked about. So it's going to be 10 probabilities for each class. Yeah, so to build the, let's see, this is where I generated the frog images. I won't skip too far ahead. Yeah, so these are just the frog images to give you an idea of like the distribution. So if you want to turn that process around and start with a vector and then generate an image as an output, it's essentially the exact same process, except now instead of downsampling, we're upsampling. Or we can add a convolution transpose layer as well. So in addition, yeah, I'm using func tools again to add a really nice leaky ReLU. I'll put a note there. Yeah, so the leaky ReLU just, instead of the standard ReLU, which is flat before 0, that standard leaky ReLU has a slight slope. And so that's the only difference. So we're just like in one line, just like defining this like useful variant of ReLU. And again, this is just so that we can actually preserve that gradient in our discriminator. And so we're going to build the discriminator the same way. This time I'm going to add in batch normalization in between. But otherwise, it's the exact same. The only difference is that instead of a 10 class classification vector, we have a 1 class classification vector. Because what are our 2 classes in this case? In the discriminator's case? Yes, exactly. It's real or fake are our only 2 classes that we care about. And here you can actually see for the generator exactly that process that I talked about in the slides. So we have this first block to take that input vector and then reshape it into like a convolutional shape. So 4 by 4 by 50. We're going to batch normalize it and then upsample it. And then now we get into these convolutional layers as well. So it'll be a little bit easier to see when we print the summaries. So yeah, you can sort of see here that it's going through the exact opposite process, where it's starting with that vector and then building it up to something exactly the same size as our image. Trivia question, I haven't actually talked about this. Does anybody know the range of output for tan H? -1 to 1, yes. So if we didn't know before, that's actually why at the very beginning I scaled the images from -1 to 1. So we have an activation function that easily maps onto that exact same range. And so that's the very last part of the generator, is just scaling it appropriately. Yeah, and so the important part about this, we're actually going to build these two models. The very first one is the discriminator, and that's quite easy. We just like take in an image, and then we're using binary cross entropy because it's a binary classification. For the discriminator, we're going to combine the models, but we're going to use the same thing. It's going to be the same loss, like the same output as the discriminator. So here you can see we're actually we're defining like new layers here, an input layer, an image layer, and then we're actually passing that through the discriminator model here. And so this is, I sort of titled the talk keras plus TensorFlow. And the reason is because like in secret right here, we're actually manipulating TensorFlow tensors. And it's not, it might not be crystal clear, but let me. So yeah, oh, that's a model. Let me build this and I'll show you. You can see. So if we run this, so what we're building here, when we take this like keras input and then wrap the generator around it and then get the output of that, the output image, what we're actually plugging into is a TensorFlow tensor. And so all of this, we're actually setting this up using TensorFlow, just kind of behind the scenes. But yeah, we can still do that. We just need to start with a Z and then end up with that valid indicator, and we need those to connect. And if you doubt that they connect, you can always see, did I call it plot model? I believe I did. You can see what that looks like here, where we've got the noise input of 100 dimensions. We're passing that through that sequential layer, which is our generator, and then we're passing that generator through our other sequential layer, which is our discriminator. Cool. And then now we, unlike before where we can use keras's handy like dot fit, we're going to have to do this a little bit by hand, but the process is not that tricky. So I'll step through these lines of code really quickly with you. The first one, like we asked, how do we generate similar or the same images each time? We do that by generating the same set of random normal vectors before we ever start training, and we just keep that. So that's our noise sample, and we'll use that to generate samples of noise periodically. I'll run this while I'm talking about it. Oh, TQDM does not work. So yeah, if you're trying to run this and it doesn't run, you'll have to change this line. This line right here to TQDM instead of TQDM notebook. So my apologies for that. But yes, so we're generating this once, and then as we run through training, we're not regenerating it again, and that's going to let us sample images from the generator as it improves. We're going to run through several epochs. I've got 10 to start out, but you can obviously change that. And then for each step inside of that epoch, we're going to generate a new set of indices for our examples. And we're going to use that to build our batch of our input data. And then we're going to generate a batch of noise, and that changes every time we change it or train it. And then we're going to generate an image from the generator. And so this is all going to be our input to the discriminator. So we're going to train the discriminator twice each time around. Once on the on valid data. So that's going to be valid is just a list of ones that I generated here. And then we're going to generate it on fake, and the Y for fake is just zeros. So we've got this X batch, that's our training data, and we're saying like you need to guess 1 for that. And then we've got the generated data, and we're saying you need to guess 0 for that. And then yeah, and so it's a similar process, but we just do it once for the combined model for the generator and the discriminator. And for that one, we just give it noise and tell it whatever you produce with noise, you want to get the discriminator to guess 1. And so what it outputs, that's going quite slowly. Interesting. That must be because we have there are a lot of people on it. It was going quite a bit quicker earlier today. Yeah. So if you run this on your own time, that's interesting. It was going significantly quicker. Yeah. So I don't have much control over how quickly this runs because it's Google's servers and not mine. But yeah, if you run this in the background, it'll sort of it'll every 10 minutes, I guess, it'll start sampling those, and you can see it improving quite a bit pretty quickly. All right, the last thing I wanted to cover really, really quickly, so that if anybody wants to experiment with the spectral normalization layers and the auxiliary classifier, I've got all of that in this notebook. So I'm going to skip ahead to notebook 2. So that's like the middle notebook is sort of very similar to this one as well. So yeah, this is the notebook that you'll need if you want to get the data sets that I put together. It automatically downloads them and unzips them, and that actually runs pretty quickly. You'll also need to, I've got a line in here that requires an updated version of keras, so you'll need to run that as well. So while that's sort of cooking, I'll talk a little bit about some of the differences here. The main difference here is that I have this custom library that we actually download from here, so we can go ahead and look at that library. So yeah, this is just standard Python code where we're adding the spectral normalization to convolution, the 2D convolution in keras. And you can see right here, if you want to go through the math, if you want to tweak this at all yourself, you can. But yeah, all we're doing here is we're actually going through, I just went through that spectral normalization paper and then added this computation for every convolution. All right, and we can see that that worked. Let me... All right. Yeah, if you get an error right on this block, it's because I expected you to download the soph.py in the previous notebook. So you might want to run that from the previous notebook if you get an error there. But the really important thing I wanted to show everybody, I guess there's two. One is a fairly new way in keras to load in data from a data frame. And that actually is really helpful for the task of multi-label classification. And so that's, keras has a data generator here, and then we're just passing it a data frame. And so this data frame is a list of all of our images, the file names of them, and then the attributes. So whether people have 5-buck shadows, or big lips, or wavy hair. And yeah, we can so just pass that directory and then this data frame, and then it automatically generates batches for us from that. And we can look really quickly at the architecture I built to get this to work. So here we got the discriminator. It's not that different, you can see, for these like quite a bit more advanced layers. And the reason is like the spectral normalization is hidden in that package or that file that I had you download. Otherwise, it's essentially exactly the same. I'm using quite a bit bigger filters. So you can see here going up from 50 to like 120 and from 120 down to 50 instead of fixing it just at 50. So the very different thing if you want to do the auxiliary classifier is how you set up the models. So I said we have a combined model, and that's this here for the discriminator and classifier. So this is sort of the backbone that we'll use for both of those. And I just called it discriminator base. And here is where we're going to break that apart. And so you can see, actually, we're defining two different layers. One of them is going to be a layer for the binary classification of fake, not fake. The other one is going to be for the multi-label classification of all of the celeb A labels. And so that's the sort of newish modification of the versatile auxiliary GAN. I'm using a different loss here that we didn't have too much time to go into, but this is a extremely lightweight implementation of hinge loss in keras. So that's something I'd like to write this up a little bit later because all of the hinge loss examples online are just way too complicated. But you really only need like 10 lines here. So yeah, once we define these two derivative models and then our losses, we can compile all 4 of our models. So we have 4 models in effect, but we're really just taking the discriminator and training it first for the GAN task and then for the classification task. And we're going to do the same for the generator. We're going to set up our sampling data ahead of time so that we don't have to resample each time. And then we're going to run it. And this is probably going to be slow too. But we'll see. But if it is, we can just do questions from now on. We can do questions while it's running. Oh yeah, that's the initial. Okay, yeah. So while this is running, let's talk about questions, and maybe we'll get a couple batches in so we can see it improving. Yeah.
So for the generator and the discriminator, is it just the layers are just flipped, right? Does it have to be like exactly symmetrical?
That's a great question. No, it doesn't have to be symmetrical. There's a few differences. Let me go up to this. So as you can see, I sort of have a lot more layers for the discriminator for one. And part of that's because for the discriminator, I'm breaking out the activation. Whereas, or actually, I'm adding batch normalization in the discriminator, and I'm not doing it. Sorry, I have batch normalization here in the generator, and I don't have it in the discriminator. And that's just like a strange tweak that I found that worked well. I would expect that you could actually add batch normalization here, and it would work fine. Typically, you see if you look at the parameter counts, this is at about 250,000. Our generator is much, much higher. It's well over double. So they're definitely not perfectly symmetrical. And that ends up being fine. Yeah?
So during training, it's all training from only real data.
Mm-hmm.
Is there any specific reason for that?
Oh, that's a good question. Yeah. In general, you don't have to mix it. It typically is more work to mix it than not. There's a really, really cool paper / loss function developed by, I'll show you the paper. This woman, Alexia J.M., I highly recommend looking at it. It actually explores GANs that look at the relative prediction from true to false. So it actually does mix them. And I think with typical loss functions, that doesn't provide an improvement, but she found a way to look at, rather than one and then the other, look at them relative to each other. And it actually works really well in some cases. So that's a good question. Any other questions?
Somebody had a question. I think somebody had a question up here. No? Okay.
Ooh, we might get to one more. Yeah.
So you mentioned that GANs are much better than autoencoders.
Typically.
Why do you think that's the case, and what if we consider variational autoencoders?
Ooh, yeah, that's a great question. So I'm going to cop out of that question by pulling up my favorite textbook here. Or actually, let me do the Goodfellow tutorial. Because he's got a great straightforward illustration of that. So the big difference is that autoencoders are trained with what's called typically it's either mean square error or mean average error. And what happens there, we talked about modes earlier, mode collapse. Well, you can imagine in an autoencoder if there's two possibilities. So this is images from a network that was trying to predict from one frame what the next frame would be. So if you imagine that you're an autoencoder, there might be a bunch of different possibilities for that next frame. Because you're tasked with minimizing the squared error, you're always going to be better off if you minimize the square error from like all of them relative to their probability. And so you get this like blurry image that's really like a composite of all the possibilities. Adversarial, because it specifically targets like whether or not something is realistic or not, it pushes the network to produce plausible images rather than like sort of something that minimizes like the square error of what the plausible images might be. And so that's one of the big advantages. You typically get like much sharper images. Variational autoencoders, they're sort of a middle ground between the two. And I really don't have like a great explanation for why they haven't been as successful as GANs. I know Ian talks about them a lot in this tutorial. I'd like encourage you to look into that. And it might just be that like I'm not even going to speculate. Like I don't have a good answer about why. They just haven't. Yeah, I actually started working with VAEs like before GANs a while ago and couldn't get them to do anything useful. So that's a good question. Yeah, any other questions? We got a couple minutes. Cool. Well, we can see the first. This is like not a full epoch. This is the first half epoch. And we can see it's like a little bit cloudy, but this is like where it's starting to learn these faces. And we can sort of, it's going to be at about the second quarter epoch in a little bit. All right. Well, if that's all the questions, we can just like sit around and watch this bake. And then like, thanks for listening to my TED Talk.